So the big topic last week was the whole idea of a dilution. And the big thing to remember with a dilution is that it is a ratio of concentrate or serum, and percent is parts of concentrate, to the total solution or the whole solution. So if I have a 1 in 7 dilution, of lidocaine and water, and I want to find the ratio of lidocaine to water, what do I do? Well, I'll start out with the dilution. What's the 1 in 7 stand for? Okay. Okay. Perfect. The 1 is your serum, or your lidocaine in this case. 7 is your total solution. So if I want to turn that to lidocaine to water, what's going to go in here? Perfect. Yeah, we've got 1 part lidocaine still. If there was 7 total parts, 7 minus 1 leaves us with 6 parts of water. And we could use those dilutions to change the concentration, to dilute a solution down. If we have a 48% solution and we need a 16% solution, what dilution do we need to go through to dilute that down? If you remember, the dilution needed is the new concentration over the old concentration. So that'll be 16 over 48, which will reduce to a 1 in 3 dilution. Now again, a 1 in 3 dilution, you'd have to keep in mind what that means. If you're mixing that, that is 1 part of the 48% for how many parts of water? 2 parts of water. Perfect. To get the 3 total. But then we looked at an easier, and of course we did a process where we could go through and find, the amount of the 48% and the amount of water you would add to get to a certain volume. But then we went back and we looked at a solution concentration formula that was an easier way of doing that, where we found that volume 1 times concentration 1 has to equal volume 2 times concentration 2. The concentrations could either be as a decimal or as a percent. As long as you did both of them the same, it doesn't matter. So if we have 36% solution and we need 800 milliliters of 9% solution, what do we do to mix this? Well, we have both percents here, so we just have to choose which one is going to be the first concentration 1 and which will be concentration 2. It really doesn't matter. So I'll let 36 be C1. So that makes the 9 C2. Now we need to know the volume for one of those. The 800 milliliters goes with the 9. So what we are looking for is volume 1, the volume of the 36 milliliter. 800 times 9 is 7,200. And we solve for the volume by dividing by 36. So V2 is 200, and since the 800 was in milliliters, the 200 is also in milliliters. That's V1, I'm sorry. For some reason sorry about that. For some reason my 1 became a 2 somewhere in the middle of that. So that is V1, 200 milliliters, because V2 was already 800. That's not our complete answer though. That is the amount of the 36% solution. The other piece we need to know is how much of our saline or sterile water. It's really quite simple. If there's 800 milliliters of the 9% and only 200 milliliters of the 36%, the difference has to be made up by our saline or our sterile water. So 800 milliliters minus 200 milliliters gives us 600 milliliters of saline. All looking familiar? Okay. So then today we need to look at, first of all, we need to look at how are those concentrations calculated. When we say something is a 9% solution, what does that mean? Well, there are actually 3 different ways that a solution can be measured. The most common one, probably the simplest one to do, V over V, or what we call a volume in volume solution. So if we add 120 milliliters of our medication of serum to 480 milliliters of a neutral solution, find the concentration. When we are dealing with this, we are looking at, of course, the top volume is the volume of the serum. But just like in the dilution, the bottom volume is total volume. So when we're looking at this, 100 milliliters of serum, 480 milliliters of saline or neutral solution, we need to find from that the total volume. What's that total volume going to be? 600. Very good. 480 plus 120 is 600 milliliters. So the concentration here is going to be 120 in 600. And of course, how much is that going to be out of 100? Just back to our review of our percents. So 120 times 100 divided by 600 is 20. So that is a 20% volume in volume solution. A word of warning. A volume in volume solution is not always quite that clean. Depending on what it is you are mixing into the water or whatever. For example, let's say you have alcohol, rubbing alcohol in water. If you add 200 milliliters of alcohol into 800 milliliters of water, common sense would tell you you'd have how much? 1,000. 200 plus 800 would be 1,000. Slight problem with that. Alcohol dissolves into water. When a substance dissolves into another substance, what happens is, if you picture this being the particles of the water, alcohol, the particles of alcohol, the molecules in the alcohol are small enough that they can fit in between the particles of the water. That's how it stays in solution. So therefore, when you add that 200 milliliters into the 800 milliliters, you may end up with like 875 milliliters. So just something to be careful of. When you look at the label of a bottle, it'll tell you how to constitute. It may tell you constitute, if I can spell, constitute 60 milliliters of medication with 160 milliliters of sterile water to get a 30% solution. Well, when you look at that, the math doesn't work out, does it? Because if you're looking at this, 60 and 160 add up to 220. We have 60 milliliters of medication. If we cross multiply and divide there, that will not come out to 30%. If we cross multiply and divide, 60 times 100 divided by 220 ends up being 27.27%. It's a little off. But what's happening is, even though we're mixing 60 milliliters of medication with 160 milliliters of water, we're still only getting a total volume of 200 milliliters. So when we deal with a volume in volume solution, rather than talking generally about how much serum and how much water we're going to mix together, we usually will word it like this. We will mix 200 milliliters of our serum with water to get 600 milliliters of solution. What that means is you are putting that 200 milliliters of the medication into the container, into the beaker or whatever you're using to measure it out first, and then you're just adding saline or sterile water to it until the total volume gets up to 600 milliliters. Not telling you anything about how much water you're actually going to add, because you are going to add more than the difference. You're going to add more than 400 milliliters. So now when it's worded like this, we absolutely know that there are 200 milliliters of the medication and 600 milliliters of the total solution. So now it is safe to calculate our percent volume in volume by cross multiplying and dividing to get 33.33%. Does that make sense? I know it's kind of a tricky concept, but it's that's probably the simplest way to get around is just talk about total solution instead of how much water you're going to add to it. Another common way of constituting a solution is to talk about W and W, or weight in weight, which is really quite a misnomer because the units we're using are not units of weight. Have I talked to you guys a little bit about the difference between weight and mass? A little bit. The units we use for this are generally milligrams or grams, which technically are units of mass. But we've just kind of tend to use them interchangeably between mass and weight because people don't like using newtons for force, for weight. So we are talking about weight and weight, but we're using the mass units. This one is a little simpler because if I add 30 milligrams of serum or of any medication to 70 milligrams of water, I will get a total of 100 milligrams. Unlike the volume, where the volume doesn't necessarily add up, the weight, the mass, will add up. There's no way to get around it. So when I'm doing a weight in weight solution, I don't have to be quite so careful to make sure that what I'm giving is the total weight, because the weights will add up and there will not be any slop in them. So here, I need the weight of the serum and I need the total weight. Well, I have the 30 milligrams for the weight of the medication. What's my total weight going to be? 100 milligrams. So now, of course, the percent calculation is pretty simple. 30 times 100 divided by 100 is 30. That's a 30% solution. So let's find the concentration of 80 milligrams of serum mixed into 200 milligrams of NS. I want you to try that one quick, see what you come up with. So what did we come up with here? How many of you came up with 40%? Good. So what we need here, I saw some looks of, oh no, I was hoping you didn't come up with that. And we have the serum, which is how much? 80 milligrams. What needs to go on bottom? Total, which is 280. Very good. You had to catch that 200 milligrams was not the total, it was just the water. So now we'll go ahead and set up our proportion, and we have 80 times 100 divided by 280, which comes out to be what, 28.57143 approximately. So 28.6%. Don't worry, it's not contagious. Math is about patterns, and once you see some of the, I mean, I've done this every day of my life for like 19 years now. Yeah. Have you avoided this every day of your life for about the same amount of time? Once you start seeing the patterns, the calculations are simple. You start in on a calculation, and before you get a few steps into it, you see a pattern develop, and you just go with it. I'm not saying that they're easy to find, and we'll go with that. There you go. You'll have to start adding the word savant onto the end of those names you call me on the weekend. Doing your homework, that idiot. Okay, let's look at our third type of concentration. We can have a W in V, or what's called a weight in volume. This is one that is probably the most common, most useful. It's used when you have some sort of a powdered serum a powdered medication mixed into, is going to be delivered in a fluid. So let's say we have it just in our saline again. Some medications that we would deliver would be what we would call a suspension. In a suspension, the medication is mixed into the fluid. Like I said, usually saline or sterile water. It's mixed in there really well. But if you were to let it sit for a couple hours, what we'd find is on the bottom of that cup of liquid, there'd be powder starting to settle out again. We would never use a weight and volume concentration on something like that. In fact, when you're dealing with medications, you really don't want that at all. You don't want the medication to start separating as it's going into a patient. A solution means it actually is dissolved into whatever the main substance is, usually, again, the saline. And if it is dissolved, it will stay there forever unless something forces it to come out. If you mix salt into water and let the salt dissolve into the water, you can set that cup of water on your table and leave it there for months, and the salt will stay there. It'll never settle out to the bottom if you dissolve the right amount into it. There are ways you could get it out. You could heat it up, and actually at higher temperatures, the salt will fall out of solution. That's why most of the medications that are in solution are kept at cooled temperatures. If they get warm, they'll separate. Or if you shake it vigorously, the salt can fall out of solution. But normally then it would immediately dissolve back in. So if you have a solution where the substance is truly dissolved into it, we end up with that case that we looked at earlier with the alcohol being mixed into water, where the alcohol can hide in the particles. If you have a true solution, adding that powder in, and usually in the medical field you stay very safe, where you don't go anywhere near the limit of the fluid to hold that powder. Now, if you have a true solution, that powder that you add into that fluid will not increase the volume at all. So in a weight and volume solution, the volume of the saline is pretty much equal to the total volume. Also, while working with a weight and volume solution, in the metric system, when they defined our units in the metric system, the metric system was actually pretty well planned out. It was actually done in the late 1800s, 1880s and 1890s is when they created it. So it's a lot older than a lot of people think it is. But it was a planned system. They had been measuring for centuries at that time. I mean, inches and feet developed in the 300s and 400s as units of measurement. And they were kind of put together to create a measurement system. And it's very clumsy. I mean, 12 inches in a foot, 3 feet in a yard. I mean, a lot of odd numbers to try to remember. So when the metric system was created, they wanted it to be well put together. You know, they didn't want 231 cubic inches in a gallon, stuff like that. So when they created the metric system, 1 milliliter was defined to be 1 cubic centimeter. So the definition of a milliliter is literally 1 centimeter by 1 centimeter by 1 centimeter. Whereas in the standard system, to go from a cubic inches to a gallon, it's, like I said, 231, and not even exactly, approximately 231 cubic inches in a gallon. In the metric system, it is exactly 1 cubic centimeter in 1 milliliter. Along with that, they planned out the weight of a gram. Actually, not the weight, the mass of a gram is defined to be the mass of 1 milliliter of water. A gram is pretty small. It's just a little bit heavier than a small paper clip. But it allows us then to again, go between mass and volume rather easily. Now, we're calling it weight at this point, but we are actually technically using mass. So since we know that 1 gram is approximately 1 milliliter, since we're using saline, which is water, when we mix a weight in volume solution, the weight is always in grams and the volume is always in milliliters. So we have to make that translation. So if I am mixing, let's say, 36 grams of morphine into 300 milliliters of saline, finding the concentration of that, well, it's 36 grams of medication in 300 milliliters of total volume. Remember, we said the medication does not increase our total volume here. How much is that out of 100? We will cross, multiply, and divide. 36 times 100 divided by 300 is 12%, correct? So I have a 12% solution. So if I ask you to find the concentration, and I really should specify the weight and volume concentration of 800 milligrams of insulin in 400 milliliters of saline. What are we going to do? Careful. The 400 milliliters does go on bottom. That will be our total volume. 800 is not what goes on top, though. Nope. That 800 is in milligrams. We need it to be in grams. It has to be grams over milliliters. So 800 milligrams is 0.8 grams. That's a conversion. Actually, a couple of them there that you should get good at. Grams, milligrams, and micrograms. The difference between them is 1,000, or 3 decimal places. The way I remember it is if the units get smaller, the number has to get larger. Exactly. If the units get larger, the number has to get smaller. So here, going from milligrams to grams, we're going from a small unit to a large unit. So the unit gets larger, the number has to get smaller. So we have to move that decimal point 3 spots to the left to make the number smaller. Get 0.8 grams. Isn't it? That would have to be 6 spots, yes. Yeah, if we had, let's do this one. Let's say we had 7,200 micrograms, and we needed to go to grams. Yeah, to get from micrograms to milligrams would be 3 spots. From milligrams to grams is another 3. So yes, you'd have to go 6. You have to go 1, 2, 3, 4. You have to add a couple zeros. 5, 6. 0.0072. And something we've been asked to stress is always make sure you put a 0 in front of your decimal point now. They've actually, in the last couple semesters, started marking those wrong on your dosage calculation test if you don't put a 0 in front of the decimal point. So then back up here, now that's 0.8 grams out of 400 milliliters. Cross multiply. 0.8 times 100 is 80. Divided by 400 is 0.2. So it's 0.2% solution. Be really careful with that. A lot of people are tempted to turn that into 20%. It's not. Okay. Next thing we want to talk about, and actually I just want to mention one other thing quickly. In your textbook, on page 150, there's a lot of vocabulary that I am not going to get into. It's something I'm going to let you study on your own because realistically you guys can read it out of the book just as well as I can sit here and repeat them off to you because there's really nothing mathematical about it. All it is pretty much abbreviations. Little things like Q4H. If you were to look up that abbreviation, what that means is every 4 hours. I'm not saying they're not important to us. They are important. It's just not something that can really be taught. It's just something you got to look over and be familiar with. And I'm always going to allow you the opportunity to look them up if you need to. So maybe that's a page in your book you want to mark. But it is important because if Q4H and Q6H, when we start doing our dosage calculations, and is that a suitable dose or is that a safe dose? Well, the same dose on Q4H may be unsafe, but acceptable under Q6H because it's every 6 hours instead of every 4 hours. So it is very important that we know those and are aware of them. But like I said, it's just not really something for me to teach to you. It's just vocabulary to look at. So anyway, the next thing to look at for us is we're going to look at reading a syringe. Reading a syringe pretty much all comes down to reading scales. When you go to read a scale, biggest thing is just figuring out what each division stands for. For example, if I have a syringe that is labeled like this, that would read very differently than a syringe that is labeled like this. And differently still than one labeled like this. Now, one of the first things we should go over The question always comes up, well, why don't I just use one syringe and do everything so I know what it means? We start talking about accuracy or precision in dosages. You want the size of the dosage to be really close to the size of the syringe. Why is that? Well, because a full syringe is more accurate, more precise. Let me give you an example of what I mean. Let's say that the dosage we are asked to give, we need 0.45 milliliters of medication. From what I just said, the size of the dose approximately equal to the size of the syringe. Well, this syringe down here, as you can tell, goes up to about 0.5, a little over 0.5 milliliters. So if I'm getting a dosage of 0.45 milliliters, that would be the one I would want. First thing I find, here is 0.4. That's pretty close to what I want to use. I need to figure out what each of those markings are now. So I find two markings, or two consecutive markings that are labeled. From 0.4 to 0.3 to 0.4, if I subtract that, that is 0.1 milliliter, or 1/10 of a milliliter. And then I have to count how many divisions are between them. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions between them. So if I take that 0.1 milliliter divided by 10 divisions, that's telling me 0.01 milliliters per division, or 1/100th of a milliliter per division. So now to figure out my dosage here, again, my desired dosage, 0.45 milliliters, I go from that nearest marked number. 0.4 is the closest labeled marking to what we want. We have to stay below it, of course. And we count up from there. From 0.4, we'd count up by 1/100th of a milliliter. So this would be 0.41, 0.42, 0.43, 0.44. And there it is, right there, 0.45. So we would load it up to that point. Why would that be more precise? Well, let's go to this one here. If I wanted to try to load up 0.45 milliliters on this one, I'm just going to pick any two of these. Let's go from 2 to 3. 3 minus 2 is 1 milliliter. How many markings are between? 1, 2, 3, 4, 5. I divide by 5. Every marking here is 0.2 milliliter, or 2/10 of a milliliter. Now, the very beginning of a syringe is never very accurate because usually it's tapered. So the first 1 or 2 markings usually aren't even shown on the syringe because they're in that taper. The volume is in the taper. This one I did happen to mark the 0 right on the edge there. But even so, I mean, a lot of times if you're less than that first marking, you'd have to count backwards from the first labeled mark. But here we'll even count up from 0. If this is, so at 0.2 each, this would be 0.2, 0.4, 0.6. So the required dosage that we want is somewhere in between here. Well, 0.45 would be less than halfway. So we'd be trying to load this thing up something like this. So first of all, you can see it's really hard to even see the marking and figure out exactly where you want to put it. Second, what would make it so that this syringe can be labeled differently than this one up here? Well, the reason it would be labeled differently is this syringe would probably be much wider. Well, it wouldn't probably be. It would have to be much wider. So that the same distance with this plunger is a lot larger volume than with the one up here. What that means is if we're off by just a little bit, if that plunger's out a little too far or in a little too far, the amount of volume that we're off is a lot more. Up here, since it's a narrower syringe, if we're not exactly on that marking, the volume that we're off is quite a bit smaller. Does that make sense? So the reason we want a syringe that has a capacity really close to our dosage is because of that. We want to use the narrowest syringe possible without having to stick a person twice. So you don't want a syringe that's too small because there's less error in it. A full syringe is a more precise syringe. Okay, with that, I've been rambling. That looks like a good place to take our break. So let's do that. We'll take our break now a little bit early. We'll come back about 9:25, and we'll go from there.